Okay, let's start solving this problem. Find and classify local extreme values, it says. So our function is this, x squared over 2 to the power x. So to be able to classify local extremes, we need to find critical points. So critical points, let me put a critical points. So what is the critical point? What's the critical point? It is a zero of the f prime, derivative of f, or singular point of f prime. So let us analyze. So f prime x, it is just, I'm just gonna apply quotient rule, 2x, 2 to the power x, 2 to the power x, minus x squared, the derivative of 2 to the power x, 2 to the power x ln x, over 2 to the power x squared, so 2x. So let me simplify to 2 to the power x dot x, uh, 2 minus x ln x. ln, I'm sorry, it should be ln 2. Nasıl bir şey? Aha. Over 2 to the power 2x. Okay, let us look at the zeros. So let's equate the zeros to be able to find critical points. I have already said it, but let me, okay, rewrite it. So what are the zeros? This 2x and this 2 to the power 2x never zero. So x is 0 or x is equal to 2 over ln 2. Okay, they are my critical points, only critical points. So whatever happens, they should be local maximum, minima, or neither. So let us understand their local max or min. We can do this by taking the second derivative or making some table. Let us make some table. So let me put 0 here. 2 over ln 2 here. So when this is less than 0, so this is negative, right? This x is negative, so we have minus sign. I have, since x is negative, so this is positive. So this is positive and this is negative, so it means negative f prime. So if it is bigger than 0, but less than 2 over ln 2, so this is positive. Now this is negative, right? Because it is now positive, but it is not that big. It is less than 2 over ln 2. So it is negative. Negative, positive. It should be positive because, let me analyze first. We look at it again. When it is less than 0, this is negative. So this is positive, so negative. When it is bigger than 0, it is positive. Now, but it is less than this, so it is positive, so it should be positive. Then after that, it becomes bigger, but this is positive, so this is negative, so this is negative. So it is decreasing, increasing, decreasing. So this should be local max, local min, local minimum. So this is local maximum. But are they in our domain? Yes, because our domain is all real numbers. So this means real numbers. So this is my whole domain. So this is fx. So I have found the critical points, and now I have classify them. So let's go to part B. Find absolute extreme values if they exist. Now we have some local maximality here, local minimality here, but I don't know what happens at infinity. So I don't know whether it is bounded or not. So let's take the limit. Limit when x goes to infinity, x squared over 2 to the power x. So above is going to be infinity, right? Yeah. I cannot say right away that we have absolute max or min because my domain is not closed and bounded. Okay? It is closed, which is equal to R, but it is not bounded. It is infinite, right? We have not bounded. Okay, that's why we cannot say yes. Even though our function is continuous, I cannot say that it has a absolute extreme values. So I cannot use extreme value theorem. Anyway, maybe there are absolute, maybe there is some absolute maxima because consider 1 over x, right? 1 over x on 1 infinity. Even though, close, let me close it. But this is now, this is close but not bounded. And it has an absolute maxima at 1. Done, right? Because after that it just decreases. So anyway, let's go to our original problem. The numerator going to be infinity, the denominator also going to be infinity, so I can apply L'Hopital rule. But I don't know if the limit exists or not. That's why I'm just applying. So I'm just gonna calculate the derivatives of numerator and denominator. X goes to infinity, 2 to the power x, and then 2. Still, we have the same issue. Infinity over infinity. Again, apply L'Hopital. Limit x goes to infinity. 2 over 2 to the power x and then square 2. So now we have 2 over infinity. It means this limit is 0. So it means that this L'Hopital arrows are actually equality. So my limit is 0. So maybe I can say something about this, right? So let me just calculate these points also. So what is f0? When you put 0, this becomes 1, this becomes 0. What about f of 2 over ln 2? So when you evaluate at this part, 2 over ln 2 square over 2 to the power 2 over ln 2. So maybe in this form it is not good. Can we simplify? This is not in the, okay, this is not in the numerator, yes. But I can put this as ln2a, right? Okay. Anyway, let me write it anyways. Or let me just calculate 2 to the power 2 over ln 2 is equal to 2 to the power 2 or 2 to the power 2 ln, not ln log 2e, right? When it is in the denominator, you can invert it like that. So this 2 comes to the power. So it's just e to the power 2. Okay. So it means that it is 2 over ln 2 square over e to the power 2. Right. It's just small detail. But it is strictly bigger than 0. Okay. Strictly bigger than 0. Hmm. So I have some graph. Okay, I have some graph. It takes 0 at 0 and goes to uh, some local maxima at this point 2 over ln 2. Then after that point, it goes to 0 again because of this limit, right? I have just calculated. So it means that it can be local maxima. Sorry, absolute maxima. But I'm not sure because I don't know any information about the behavior at minus infinity. So let's also calculate that. Still, we are not sure. Let's limit x goes to minus infinity, x to the power 2, x square, I mean, over 2x. I'm sorry, let me drink some water. So maybe if you are feeling insecure about this minus infinity thing, you can change the variable to x to minus u or minus x since they are dummy variable. Anyway, limit u goes to infinity, u square over not over 2 to the power u. I can rewrite this like that. So when a u goes to infinity, okay, this is infinity, this is infinity, right? And they are all positive. So I cannot say that this above is absolute maxima because at minus infinity, this limit is infinity. Or let me just write equality. So it means that before zero, it does something I don't care, but it goes to infinity. Okay. So it means that there is no absolute maximum. So by this limit only, there is no absolute. If your function diverges to infinity at some point or at infinity, you cannot say that. No, you can say that this function has no absolute maxima. But what about minima? Okay, so let's look at this function. Our function is always positive, right? This function is always positive. I mean this one. Because this is always positive, x squared, this is always positive because it is exponential. So, and it takes 0. But and before 0, it always decreases by this part, right? It is always decreasing before 0. It means that it should be absolute minima, okay? Should be absolute minimum because it cannot take less than this thing. So we can say that, however, x equals to 0 is absolute minimum, or f of x equals to 0, which is 0. Okay, absolute minimum. So this question is finished. Maybe I can show you in a graph uh, of this function. Let me to the power x. Ah, so let me copy and paste. So this is my graph. Okay, this is my graph. Look at this graph. Like I showed you, there is some local max at this point, 2 over ln2 or something like that. And this is 0. So this is absolute minimum, and this is absolute, there's no absolute maximum. Okay, that's the solution. So let's go to our next question. Let me copy and paste. Hmm, bunu çözelim. Yeah, let's solve it. Okay, so this is my question. A function yx is given implicitly by this. I don't know. It should be an exercise in one of the recitation, or we didn't even ask about this. And we have some base point. Let us approximate. Okay, this using linear approximation. So let's calculate. So my function is what? I don't have my function, right? It is implicitly given. So what should I do? I need to have, what is the linearization function? Let's remember. I have some graph like this, and I want to, let's say that I want to approximate this point on this graph. So what I do is the following. I'm just drawing a tangent line, okay, tangent line, so that when you zoom in, you get something like that. You get something like that. Zoom, zoom in. So there is some tangent line, and this. So I'm taking this part. So this part is like this. Okay. So it is zoomed version. So as you can see, you are when you are very close to this point, your points are very near to this tangent line. So instead of calculating the exact point, you can as well calculate the points on this tangent line. So this the basically the brief history of linear approximation. So what is the definition, by the way? I mean the formula, or so let me call, we are approximating around x equals to x0. Let me recall this tangent line equation. Pardon. So it is just f of x0 plus f prime x0 x minus x0. Okay. So I need to find this part. And this y4 is given. So my x0 would be 4, and this is given, right? This is okay. So I need to find this f prime at this base point 4. So I need to find y prime 4. Okay. So what should I do is take the derivative of both sides. So we have 3 y squared y prime x. There's also x, but we don't usually know. Put x here, but let me put it. Plus, what is the derivative of 3y? It is just 3y prime, which is equal to derivative with respect to x. So I'm taking derivative with respect to x, both sides. Both sides. So, okay. So it is just one. Let me make this y prime alone. So y prime x. In the parentheses of y prime x, I have 3y squared plus 3, which is equal to 1. Let me make this y prime alone. So, or let me just evaluate at this 4. Okay, evaluate at this 4, which is equal to 1 over 3y4 square, right? Plus 3. So which is 1 over 1, 3, 1 square plus 3. It should be 1 over 6. So linear approximation of my function at 4 is equal to, in terms of x. So base point fx0, which is given by 1, plus f prime or y prime 4, which is 1 over 6, x minus 4. This is your linear approximation formula. Okay, tangent line. Tangent equation at x equals 4, or linear approximation formula. Okay. Now, let's determine this. No, no. let's first finish. Y 4.1 is approximately, this means approximately, not equal but approximately, the linearization at 4.1, which is equal to 1 plus 1 over 6. Instead of x, I'm gonna just put 4.1. 4.1 minus 4. So this is exactly 1 plus 1 over 6, 0, 1. Just like 1 plus 1 over 16 or 61 over 60. That's enough. So let's solve this part B. Determine y is invertible or not. So how to determine it? Let's think. So locally it is invertible, right? Because it is there is some tangent line uh, which is not vertical. So since it is not vertical, it is graph of something. But the general why is invertible or not, I don't know. Maybe you need to work on some uh, solution of it. But maybe if I find 2x that are giving me some y value, then we are fine, right? So need to find, need to. So it means that I want to make, yx is invertible. So as you can see, so if we consider the function, okay, not need to find, okay, consider y equals x cubed plus 3x. Okay, is this function invertible? Let me draw it. Let me calculate 3x squared plus 3. So it is always strictly positive, right? So it means that it is strictly increasing. So strictly increasing. So it is invertible. Invertible. We have some theorem. If your function is strictly increasing everywhere, so it means that it is invertible. So you can put back y equals x, x equals y. It doesn't matter because when you invert something, it means that you are changing the variables from y to x, x to y. So that's why I just changed to more pedagogical form. But instead, you can just take the derivative with respect to I, y, etc. It's this derivative just explores the behavior of this function. It means that it is a graph of something, right? So it is a graph of something. So x is a graph of some y in terms of. So there is some function. Let me call g of y. So equals to x. So it means that you are looking at the variable y in x is x. So you are asking whether this function is invertible or not. But it is exactly the same as so asking the other way around. Right? So that's why it is invertible. Yes. Okay. Let me draw the curve and you can see y cubed plus 3y. Y cubed plus 3y. And y cubed plus 3y. Equals x. This is invertible. But as you can see, it goes to infinity like that, so it means it is invertible because at each point, okay, let me show. At each point, there is only one point. Okay, I mean, not like this, but let me put it in this way. At each vertical line, I have only one intersection point. At each line, I have only one intersection point. Of course, we have already shown mathematically that is invertible, but graphically you can also see it like that. Okay. Uh, so we have answered. Let me find you another question. Haven't chosen. Let's solve something which is also left exercise in previous weeks. So suppose that f has a continuous second derivative, and we have some relations, f zeros, for etc. Okay, we have bunch of relations. We need to show that this is always true. So this integral always less than one. How to show it? So yeah, it seems that we need to. Huh. Okay, it's like we have f prime double prime. Okay, here. So I also have some informations about f prime. So why don't we apply integral by parts? Try by parts. So let me call this integral I. Okay. So I can be written as, by the way, let me choose this du and dv here. So this is obviously my du. Let me call it v. And also recall integral by parts. What was it? It was if you call u dv, if you want to calculate this integral, then it means that it is equal to uv as a multiple. They are multiplied minus v du. Okay. Is actually taking the integral of both sides in the product rule of derivatives. Okay, u v in what is the derivative of this? U prime v plus u v prime. If you take the integral of each side, you get this formula. That's all. So what is this integral? It is with respect to that, it is dv is equal to f prime, u is equal to f prime. So fx and f prime x. Okay, we need to evaluate at the boundaries f0, 0 and 1. Since it has already have some, more bigger than one order derivatives, it is continuous, so you can just evaluate at this point. There's no need to take limits. That's what I'm implying. So this is a proper integral. Okay, minus integral, I'm just applying integral by parts, minus 0, 1, 1, f prime x, f prime x dx, right? Because dv is now becomes f prime, u is becoming f prime, so let me rewrite it or just equate it. There, it is very easy. Just evaluate at this point. f1, f prime 1 minus f0, f prime 0 minus 0 to 1. So this is just f prime x squared, right? Just f prime x, consider as a function, squared dx. So if you have some integrable function, which is in this case, it's a continuous, so it is integrable. And if you are calculating a square of some function, it means that it is always positive or equal to 0. But it means that this integral is always bigger or equal to 0. Okay. So what about these points? F1 is 3. F prime 1 is 7. What is F0? 4. F prime 0, 5. So it means that this is bigger or equal to, okay, no, not bigger or equal to. So let me just calculate this difference. 21 minus 20, it's like 1 minus 0, 1, f prime x squared dx. So it is always less than or equal to 1 because this is always positive or 0. Okay, that's the proof. Ha, bir dakika. Yani şöyle bir şey yapalım. Let me calculate some integral by parts. Let me find some question quick. İskilisinden tamamdır bir şey. Bu olsun canım, ne olacak? Divergence'ından gösteririz. Ya da 1 second. Okay, ben uyduracağım. Okay. Let me copy and paste this problem. Evaluate. Okay. Hmm. We are going to calculate this thing. But why? Because the motivation, first motivation before calculating our motivation is as follows. Now let's remember that if you have some polynomial over, let me call uh, x minus a to the power r1. Let me x minus b to the r2. And let me call some irreducible degree 2 polynomial x squared plus 4. Yok, 4 olsun. Or x squared plus cx plus d squared. Squared r3. Okay. So how do we express this in terms of partial fraction decomposition? That's my point. We don't care about syntax. So let's also assume that degree px is less than or not, it should be strictly less than r1 plus r2 plus 2r3 because it is degree 2. We have uh, 2r2 degree here, r3 degree here, r2 degree here, r1 degree here. So their summation should be bigger or strictly bigger than px. Assume this happens. So it's just technicality. But how do we express this as a partial fraction decomposition? So it is like equal to. So we have linear term, right? We have two linear term. Let's start with one of them. Okay. So it's just a1 over x minus a plus a2 x minus a square plus blah blah blah a r minus 1 x minus a r, or it's r1 minus 1, it is r1 minus 1 plus r a r1 over x minus a r1. Okay, these kind of things are just corresponding to this part. So these things are the partial fraction decomposition of this thing. Okay. Actually, it is px over this thing, but whatever. 1 over this thing, but whatever. Plus, now similarly, let me put this for the second linear term, but they are the same, right? I just put it to look like randomized. So that's why I'm just gonna have B1 over x minus b, B2 x minus b squared, blah, blah, blah, BR2 over x minus b to the power R2 because of the degree R2. Okay, so this corresponds to this. So plus, so we have, let also assume this ends x squared plus cx plus d has no real roots. Real roots. I mean irreducible. Irreducible. Here it means in the fields it's, and if your degree is 2, it's equivalent. Yeah, or in equivalent way, it means that c squared minus 4d should be less than 0. Okay. They are just equivalent. Anyway, how do we express as a partial fraction decomposition? So let me make some space. So plus c1 x plus d1 over x squared plus cx plus d plus c2x plus d2. Okay. So since my irreducible degree is 2, I need to put always 1 degree less. So it should be always 1 degree, but not everywhere. It should be everywhere, okay? Because here my degree is very big, even though I'm just putting constant. So here it is x squared plus cx plus d squared plus c3. Let me put this x squared plus cx plus d cube plus dot dot dot until CR3 minus 1 plus x plus dr3 minus 1 over, because my degrees are 3, over x cube plus, not cube of course. Let me make this space. I'm confusing myself. X squared plus cx plus d to the power r cubed minus, not r cubed, r3 minus 1. Lastly, cr3x plus dr3. This is just a constant. R3 is index. Okay, that's all. So instead of R3, you can put K, etc. and just formalizing. So lastly, your degree must be the full. It must be R3. As you can see, this corresponds to the last one. Okay, so this corresponds to this part. So let me put it in the some. Okay, huh. The meaning that, okay, the reason the reason that we apply partial fraction decomposition is that is that because each part, for example, this part is integrable, is easy to take the integral, definite integral. Okay, that's the reason. So as an example, so let me just calculate this part. So this is my motivation, okay? So that's why I just put it. So in general, we can solve it. Let me solve it. So, uh, So first let us separate it. Okay, you can separate this integral into two. One of them is ax, or let me put this a before x dx over x squared plus cx plus d plus b dx over x squared plus cx plus d. Okay, let me call these two are I1, I2. So let me solve this I1. Okay. By the way, if there are just some constants, 1, 2, 3, etc., it is very easy to calculate. What I'm doing is to solve them in more general way. It is the most general way. Okay. I'm going to show that what we are expressing decomposing partial fraction decomposition because at each part we can just take the integral very easily. That's my point. Okay. So let's calculate. So uh, let's call, okay, let's call, so let me dot, let's call u as x squared plus cx plus d. So what is your du? It is 2x plus c dx, right? So instead of x, maybe I can write, let me see, okay. Probably I can make this as, okay. So before that, let me then decompose this integral. So actually rewrite them. So this integral, maybe it is easier. Okay. Maybe let us first separate into two. 2x plus c and this thing. Okay. So 2x plus c. So it means that I need to put plus minus 2x minus c plus ax plus b. So this is numerator. So I'm just rewriting this integral, original integral. Okay, don't consider these things. I'm gonna do, but not right now. So it is x squared plus cx plus d dx. Okay. So it will be just this part will be u prime over u, right? So that's okay. What about the rest? Hmm. The rest is annoying. I need to get rid of this x. I can always do this, but because when I get rid of this part, I can still have some x's. Okay, maybe it is better if we solve a it's exercise. Okay, exercise. I don't want to make some case by case solution. So let me solve some similar quest. For example, 2x plus 1 over bu 2 olunca hile yapmış. Let me correct it. Okay, x plus 1 over x square plus so it should be reducible. So so it is 2x plus, so base square minus 4, it's 4. So 4 2 square 4 less than minus 4. Okay, so it is irreducible, right? Exactly. So let me calculate this integral. So it will be the same, okay? So let me call u as x squared plus 2x plus 4. You will see the algorithm, okay? Du, which is 2x plus 2 dx. So this integral I just equal to hile oldu yine. Let me correct it because it is exactly two times, so it's not good. So let me put 3. Ah. I am just making this more confusing than okay simpler work because it was very simple. Anyway, so I need to make this so x plus 1. Okay, so it is just so du over 2 is just x plus 1 dx. Okay, instead of x plus 1 dx, I'm just gonna put du over 2. Huh. Now you see the algorithm. So instead of x, so I can write x plus 1 dx plus 2 dx. Huh. Now it is okay. Over x squared plus 2x plus 4. So it is now separated into two integrals. Okay. One of them is x plus 1 dx, x plus 1 dx over x squared plus 2x plus 4. And the other one is just a constant, 2 dx over, I'm talking about the numerator, x squared plus 2x plus 4. Hmm. Now this is easy to calculate because it's just integral of du. By the way, there should be some 2, right? Yeah, this should be d over 2u, right? Because x plus 1 dx should be du over 2 by these calculations. Okay, so this is now equal to 1 over 2 ln. Instead, yeah, I'm gonna write u, but this thing means, okay, let me write. What is u? It is x squared plus 2x plus 4. Put the constant. So this part is finished. Now I am only focusing, it means that I am only focusing on this constant numerator part, right? So, so let's solve integral, yeah, either 2 or whatever. Let me call dx over x squared plus 2x plus 4 because either you solve this or the twice version. You can just multiply by. So, and this trick is the completing to the square. So it should be dx over. What is the square version? It is like x plus 1 square, right? Because I'm completing the square with respect to this linear term. Because when you expand, there will be 2x and x squared, so they will be, this part. I don't care about this. I can always add and subtract. So what is the residue? Residue is 3, so that's all. So as you can see, when you make some substitution right now, it will be the integral of arctangent. Okay, so it will be like 1 over 1 plus x squared or u squared, whatever the, but in this form, it is not good because I need to have 1 here and other something something square. So let us divide or take the common parentheses in terms of 3. So it is just 1 over 3 dx 1 plus x plus 1 over square root of 3 square. Okay, this integral is equal to this. Now make this variable change. Substitution. Let me call x plus 1 over square root of 3 as v. So it means that dx over square root of cube, say 3 is equal to dv. Let me put everything inside. So this integral is equal to then. So this integral is equal to then, or this one, whatever. 1 over 3, okay. Uh, so instead of dx, I'm going to put square root of 3 dv over 1 plus v squared. So it is like 1 over square root of 3 arctangent v plus c, some constant, which is equal to, let me put back the original variable because what is v, right? The original question is asked on the variables x. So it is square root of 3 arctangent. What is v? This is v, x plus 1 over square root of 3 plus some constant. As you can see, this kind of integral is like some part of arctangent, blah blah, plus some ln part. And usually ln part is just blah bir şeyler. Something like that. Some arctangent part and ln part, okay? So you can always do this. And if the degree of the denominator is, okay, look at the partial fraction decomposition. Hmm. You can all, yeah, these things are very easy, right? I'm not even talking about this. If you are looking at the decomposition of a linear term, this this is the corresponding decomposition. But as you can see, each part is like ln, right? Or some polynomial. Just make the variables change x minus a to u here. So it will be just x minus a to the power one more and just divide it. Yeah, these are just polynomials or ln. Tamam. They are just very, very easy. What about this? Okay, we have just solved this. But how to solve this integral, right? When your degree is one more, what should you do? What you should do? So again, you should make another variable change. Put this inside as u, and let me show you how, and the rest is exercise. Let me show you how. So let me show you x plus 3. Let me take the same numerator over x squared plus 2x plus 4. It is irreducible. Let me take the square. So let me change the variables, right? So du is actually 2x plus 2 dx. Let me put everything back. So this integral, so let me call it j now. So j is equal to, uh, still recording, okay, no problem. So this j is equal to what? Du, okay, it's like du, the same thing actually, x plus 1 dx. So it is like dx x plus 1 over uh, square plus 2x plus 4 square plus uh, 2 dx over x square plus 2x plus 4 square. Now, this part will be equal to uh, integral du over u square. As you can see, this part is just polynomial, right? So this integral is actually minus 1 over u. So this part is okay. What about this part? So let's also assume that you are completing to the square, right? So let me put it like this, like equal to this integral equal to neyse 2 dx over x plus 1 square plus 3 square. Again, now you can put back the same thing, right? You can do the same thing, or just you can put that x plus 1 is u, right? So what you get is some constant over some polynomial, or plus of two positive things. So what you can do is to maybe you can, yeah, now it is not arctangent right now, but maybe you can put u plus, let me think. I never actually thought about the second degrees or more, but it should be very easy. Since I'm not making this review video, I cannot think in front of you, but u square plus 1. You can always put u square plus 1 square. Hmm. Should we always have some integrals? And maybe you can put what are the summation of two. Ah, maybe you can apply tangent. Okay, maybe okay. Okay, let me put in this way. Let me put okay. Let us try, I don't know. X plus 1. Okay. Let me put this as a square root of 3 tangent. Tangent uh, t, let's say. Okay, when you take the derivative, dx is equal to square root of 3 second square t dt. Okay, so let me also call this integral. I'm not taking 2. Okay, let me call this integral k. So k becomes, instead of dx, I'm gonna put this thing square root of 3 second square t dt. In the numerator, I have uh, 3 tangent square t plus 3. So it means that I have 3 in the parentheses of 3 tangent square t plus 1. Okay, that was my aim actually. So what is tangent square t plus 1? It is just second t, right? So this inside of the parenthesis is just second square t. So now this is equal to 1 over square root of 3. Uh, they are cancelled. I am also forgetting this square. So there should be some square. Nope. Now it is just second square. So at the end I have what? Dt over second square t. Or it is very easy. Second means it is 1 over cosine, so it is cosine square. Cosine square t dt, which is very easy to calculate because I know that cosine easy, right? Let me put easy. Okay. So because 2t cosine 2t is equal to 2 cosine square t minus 1. So it means that uh, cosine square t is actually 1 plus cosine 2t over 2. So instead of cosine square t, if you plug this thing, it is just some constant plus cosine integral, which is sine. Okay, so it is easy to calculate. As you can see, if you are stuck, you can also try this trigonometric substitution. And I think that since everything should be in this similar form, and as you can see, for example, if this degree, as you can see, this degree is only affects at the end. So if this degree is 3 or more, right, we have deal with this 2. What happens? If this is 3, now we are taking the third power of second square, right? It means that at the end, I will end up with cosine 4t dt. So, so it's like solving. So it's like for every k, integral cosine 2k t dt is solvable or not in this closed form. And I think it is yes, right? Because I'm not sure. Let me see. Hmm, cosine square t in kth power et. So instead of this, I'm just gonna write, that's yes, solvable. You will understand not right now. 1 plus cosine 2t over 2k power dt. So now, if you expand this, what happens? It is just, yeah, it is just k power of something. So it's like binomial açılım, right? Binomial expansion. But at each time you get some cosine to the power t, k. If k is always even, you can go back to the cosine case, which is solvable. If it is not even, if it is odd, k is odd, then there is some one cosine more. Other cosines can be transformed into sinus, and this one extra cosine can be as your du, as your sines are u, then it is also solvable. So I mean that at each case, this integral is solvable. And let us recall what was this integral. It is coming from this some constant over x squared plus some irreducible thing, right? And the powers. So as you can see, they are all solvable. And because first parts are always easy, right? If it is not 2, if it is 3, then you get some 1 over minus 2 over u to the power 2, etc. So these parts are always solvable. These parts are also solved by this idea. So let's go back again to do decomposition. We have already talked about this linear terms are solvable, right? So we have now shown that this each part of this partial fraction, right, decomposition is integrable in closed form. So it means that when you have some decomposition in our partial fraction decomposition, every part, everything